Hello, Matt, or are there others? Okay. Sorry, Matt. Hello, Matt.
Hello.
Hello, Jeremy.
Hello.
Good, sir. Is everyone there? 1, 2, 3, 4, 5, 6. One of us is missing. France. Oh, Christian. Okay. So we have homework due on Friday. Notice that most of the stuff that is there in the homework is being done in the class. So you should be able to go through it and pretty much write down the same and get it done. But that also means that don't make straightforward mistakes. Like, so I'll be picky on grading, but if you follow the class so that it's hard to do mistakes. So be aware that homework is pretty much exactly based on the classroom stuff. And the last problem we'll be doing it today. Except probably the last problem. Yeah, the last problem I think is you will have to do that on your own. But that is typically you do that in introductory level physics courses. So look up your introductory physics notes and you should be able to get that. But, as midterm 1 on February 19th. I think that's about 3 weeks from today, I suppose. not today, but from Friday. Okay. Any general questions you might have? So I want to keep going along the lines we were working on. We were talking about a charge in a magnetic field, and then we started introducing the electric field. Last time what we did was we introduced the electric field in the direction of the magnetic field itself, so they were parallel for that matter. Today we want to keep that perpendicular, so keep the electric field perpendicular to the magnetic field, and then find out what is the motion. And as Christian observed last time right away, that it will actually drift in the perpendicular direction, and when you drift a circle in the perpendicular direction or in the plane of the circle itself, then that's like a bicycle wheel. If you put a small LED light on a bicycle wheel and you follow its path, it's called a cyclone. So that's what we will find as a result. But let's see how we build the problem. So this is. Let me know if it is getting harder to read. I think we'll see if I have more zoom power there or not. But let me know how it is. At least I can focus on one board instead of going all over the board. But do let me know. So we're talking about charge, positive charge in a uniform B and uniform electric field, but now the electric field is perpendicular to the magnetic field. Is that a common usage? Familiar usage? This means perpendicular to the, so the two quantities are perpendicular to each other. Okay, so again, this represents the magnetic field coming out of the board. That's your X, that's your Y, and let's say to begin with, the charge is right at the origin of the coordinate system. So I've specified E and B. So let me choose my magnetic field to be in the direction coming out of the board. So it is 0, J plus 0. Okay, so that's your magnetic field. And electric field now, I had to choose it perpendicular to that. I can choose either X or Y direction, or for that matter any way, but it's convenient to choose along the axis. So that's your electric field. Again, uniform. Oh, that's your electric field. So it's along the J direction or the Y direction. So that's 0 I plus electric field in the J direction. Oh, I meant magnetic field to be that, should be something. Okay, and we have to put some initial condition. I said we'll start from the origin. So the position of the charge at time t equal to 0, we will say is 0 itself. The vector, it's at the origin itself, and the velocity at time t equal to 0. Earlier, it was necessary to give it some initial velocity because otherwise it won't experience any magnetic field at all, and then it will just stay there at rest. But now I can still put it 0 because the electric field will make it move, and the moment it starts moving, then magnetic force will come into picture. So it is not necessary to actually put an initial velocity. So I'll say it's convenient to put 0. So it's at the origin, at rest to begin with. And then I switch on both the electric and magnetic field, and we want to ask how does the charge move around. The equations
Or how is it? Is it readable? Right? Okay. Okay, good. Our equations are mass times acceleration. It is convenient to write the acceleration as derivative of velocity with time, as we saw in the last classes. That's equal to q v cross v, but now there is an electric field also, so it is q times the electric field. This two forces combined together, that's called the Lorentz force in general. We did last time divide it out by m immediately, so that's dv by dt. That's equal to q over m by v. I will call that v crossed with a cyclotron frequency, as I written as a vector. So that's cyclotron frequency is q over m times v. And there's one more here, so it is q over m times e also. So let me call that AE. So that's the acceleration contribution from the electric field. So that's AE. Again, as a vector, acceleration contribution from the electric field is in the direction of electric field itself. There's one more quantity we can define. One is, of course, the cyclotron frequency magnitude. We can also define the magnitude of acceleration over omega c. Right? And what would be the dimension of that quantity? Acceleration divided by angular frequency. And acceleration is length over time squared, and frequency is only 1 over time. So there's a time also remaining, right? Right?
Yeah.
Like acceleration is length over time squared, and frequency is 1 over time. Right? The time cancels out, so there's a length over time remaining. So that seems to be a velocity. Okay, good. So that's like a velocity, and in this actual expression, if you were to do this, is the magnitude of the magnetic field over the magnitude of the electric field. And that's indeed a velocity if you have, quiz, right? If you want to design an experiment where you want only charged particles with specific velocity coming out of a beam, then what would you use? That's called a velocity selector. Right? So let's call this V naught. So this is the idea of a velocity selector, or this shows up in a velocity selector. Basically, the idea is that the ratio of magnetic and electric field has a velocity component in it, because you can see it in the Lorentz force itself. But the quiz is look up a velocity selector. The idea is if you were to, typically in experiments, you first want a beam. So how do you get a beam of charges? You'll take a box, basically a volume, and heat it up. Give it enough energy, so just heat it up. That's a flame. Then they start moving around everywhere. All the charges are extremely high energy, so they start moving around. Then you make a small hole in here, and they all start coming out with all velocities, like all possible velocities. They will start coming out. Keep a small hole in front of it, and this gets only the specific ones that are moving in this direction come out. Keep another one out there, and that's a beam of charges coming out. These are typically, because it's high energy, they get ionized. So these are ions, a beam of ions coming out. But what is the velocity of each of the charge in here? You don't know. It could be anything. If there was a slow moving charge here, it will be moving very slow. If it's a high moving charge here, it's going very fast. But then you're doing an experiment here. So let's say you're putting a magnetic field and you would like to do an experiment here. You would like a very specific velocity of a beam coming out. So you want to filter everything that does not belong to that particular velocity. So that's called a velocity selector. So you want to in between keep a velocity selector. How would you do that? So you will make, so this is a tube-like structure. So this is basically a tube. Have an electric field going perpendicular. That's your electric field. And let's have a magnetic field coming out of the board or going into the board, doesn't matter.
Maybe move the camera a bit.
Oh, man, camera. Sorry. Forget that. Move a camera. Quiz. Okay. Did you guys get the point I was talking about? Okay, let me try to repeat. So I was talking about velocity selector. So typically you're making an experiment, you have charges, you collect them in a small box, heat them up, they all come out with random velocities. Make two, this is called a collimator, basically a metallic object plate with a hole in it so that only the ones that are going in that direction come out. Pretty straightforward setup to prepare, except that alignment might take some effort. So you get a beam of charges and they're moving with all random velocities because one could be slow, one could be fast. And for an experiment you want to do somewhere to the right, you would like very specific velocities coming out. So what you would do is, this is called a velocity selector, put an electric field and a magnetic field. Now let's see what happens to this beam of charges, these are charged particles. Because of the electric field, they will all start going this way. And, oh, I should switch the electric field, right? So switch the electric field to go down. So because of the magnetic field, they all go up, assuming that they are all positive charge. And because of the electric field, they all start coming down, right? So one force is pulling down in the left direction, one force is pulling it in the up direction. But if you were to choose your electric field and magnetic field to exactly satisfy this relation, like the charges balance out, and that is the velocity v is equal to E over B. So based on the ratio of E over B, there is always a velocity which will go straight down out of this barrel, and they won't get deflected either down or up. If you are going faster, then the magnetic field is larger, then it will go. So if you're going faster than this velocity selection, it will go and hit up. If you're going slower than the velocity selection, it will go and hit down. Right? Either way, you will get selected, and if it is long enough, the beam that comes out on the right, that has a pure velocity. That's called a velocity selector. That's pretty much what we are talking about here. So that is such a coefficient if you want. But the quiz is about, think about what a velocity selector and how you can use it, how it is useful. This was there back in 19th century, like early 19th century. Okay, so let's that and okay, so our equation is, oh, there was a E over B, right? So E over B has the unit of some velocity, that's called. That's our setup, and let's split this into three directions, right? So we have dvx over dt is equal to the x component will be equal to Vy times omega c. Is there an electric field in the x direction? No, right? There is no electric field. No electric field in the x direction. That's 0. That's 0. So that's only equation. What about the equation in the y direction? That's equal to minus Vx times omega c, right? And now there is also a force from the electric field. So that's equal to plus AE. That's the change that's happening with respect to the magnetic field. Earlier, we didn't have this expression, and we want to see how that happens. And velocity in the z direction, or acceleration in the z direction, that's equal to 0 because magnetic field is in the direction of z, so the cross product doesn't contribute, and there is no electric field, so that's equal to 0. So velocity in the z direction is a constant, and let's see what is that at t equal to 0, so that's equal to 0 itself. Right? It's supposed to be a constant, but it is 0 because we started with the initial velocity 0. So that means this implies that the motion is in 2D plane. Right? So this is in a plane. So we are worrying about only x and y direction. That's our two equations, and let's try to work on that. So, okay. Immediately we will try to substitute one into the other. So, or take the differentiation, right? So let's try to d 2dx over dt squared. So basically, I start with the first equation, take the derivative with respect to time. So that's equal to omega c times dvy over dt. But the derivative with velocity is nothing but coming from the second equation. That's equal to omega c times minus omega c vx plus acceleration from the electric field. And that's our equation. So we have second derivative with respect to x over dt squared is equal to, I can write this as minus omega c squared and vx minus of ae over omega c, which we said was e over b, right? So this is e over b. Remember, ae over omega c is e over b. That's our first equation. The second equation, I can actually rewrite, so to do something immediately. Let me call Vx prime, let's say, is equal to Vx minus E over B. That's a momentary transformation I do. That way, when I take the derivative, this is a constant, so that doesn't mean anything. So derivative will be the same. So if I were to write in terms of primes, this quantity is Vx prime over dt squared is equal to minus omega c squared Vx prime. That's nice because I know how to solve that equation. That's a solution that we already know from last class. So that's equal, we know how to solve. Okay, so that's going back to the Vy. Let's see what happens. We'll do the same thing. So first we'll be on this. All right, we want to begin from there. So let's go to the Vy. So that's second derivative of y with respect to dt squared. So basically, I'm taking the derivative of the second equation. If I take the derivative of the second equation, the acceleration term is a constant, that doesn't contribute. This is basically equal to minus omega c squared times Vy itself. So Vy remains exactly the same as earlier, right? There is no change at all. So that's your second equation. We know how to solve this. Move this. We can solve this. This is Vx prime as a function of t. Can have two solutions: a times cosine omega ct plus b times sine omega c times t. And Vy is an independent equation that's equal to c times cosine omega ct plus b times sine omega c t. But if I take the differentiation of the first one, it doesn't matter whether it is Vx or Vy because the derivative of this is the same. So dvx prime over dt is equal to dvx over dt, even though there is this constant sitting up there. If I were to take the derivative, so that's dvx prime over dt, which is the same as Vx over dt, divided out by omega c also, I get minus a sine omega ct, this is what we did last time, plus b cosine omega ct. And that's supposed to be equal to Vy. If that is the case, then we should be able to equate these two. So that means C has to be equal to B and D has to be equal to A. So we learn that D is equal to minus A and C is equal to B, which means our solution is Vx. I can further tell that because we know the velocity is at time t equal to 0, I can also say that setting the let's see. First let me do this slow. So Vx prime, which is Vx minus EB, right? Vx minus E over B is equal to there's a confusion here, right? This is a B, not the magnetic field. Okay, that's hopefully not very confusing. Right? This is a coefficient, constant coefficient, and that's a magnetic field. Okay, so we need to try T bar, let's say. Okay, sorry about that. T bar shouldn't confuse because we do this all the time, right? So, and this is B. Okay, Vx minus EB is now equal to A times cosine omega Ct plus B times sine omega Ct, and Vy minus 0 if you want is C is B, so that's B cosine omega Ct plus or minus, right? Minus A sine omega Ct. Let's see what happens at time t equal to 0. So at time t equal to 0, Vx is 0, so that's minus E over B. And at time t equal to 0, sine goes away, so that's equal to A. So we know that A has to be equal to minus E over B. This is slightly different from what we did earlier. Earlier we used to have an initial velocity. So whatever was being done for the initial velocity, now the role is slightly different. And at that time we had initial velocity, that was an initial condition which was slightly different. So in that sense, the equations are slightly coming out. Coming for the Vy, so that's 0 minus 0, that's equal to B want is also 0, right? So b minus 0. So b is equal to 0 and a is equal to minus a over b. So this is conditions are. So b is equal to 0 and a is equal to minus e over b. So let me put this all together. I'm going to erase some parts so that I don't have to go all the way that side. So I'm afraid that you won't be able to read. Okay. This equations can go. This is fine, I suppose. Okay, so our solutions are I'll put this all together. So Vx minus E over B is equal to A is surviving, so that's minus E over B cosine omega c t, which means let me write it as Vx as a function of time is equal to, take it on the right hand side, that's E over B, which is a velocity. Remember, that's like a, it's not the initial velocity. Initial velocity, remember, is 0. Negative ct. And Vy as a function of time is equal to, B doesn't contribute, so it is A sine omega t, but A is minus, so it is again E over B sine of omega ct. Okay, so that's our velocities, but still we are worried about positions. Right? So let's take the derivative, integral again. So remember, this is dx by dt, and that's dy by dt. Hopefully, it's not going out of the board. Integrate it out, so this becomes x minus x at time, so x minus some integration constant, so that's x minus x naught is equal to e over b times t. So this e over b times t. Let me call this v naught for the time being. Like, remember, we defined that. So that's e over b is v naught, right? So that's v naught times t. Because when I integrate 1, I get a t. When I integrate cosine, I get a sine, but with a positive sign, so that's plus v naught over omega c times sine omega ct. So again, let me clarify. So this is E over B here. I'm going to use E over B as V naught, and V naught over omega c now, right? That's V naught will be the radius r, right? Similar to what we had earlier, but radius r of what? It will turn out to be the radius of a circle. You'll see what kind of a circle, right? So maybe switch back to V naught here, right? Because already there's a V naught. Sorry, I keep switching things around. Okay, at time t equal to 0, what happens? At time t equal to 0, right hand side is all 0, position is 0 because it starts from the origin. So an initial condition implies that x naught is equal to 0. So this is not bad. Because of the initial condition. Do the same thing for velocity, so y direction position, so that's y minus y naught is equal to when we integrate sine, that's a minus contribution that comes in. V naught over omega c times cosine omega ct. At time t equal to, and this is again radius we're going to define. So at time t equal to 0, y is 0, so you get 0 minus y naught is equal to minus r. So that means y naught is equal to r. So what we have here is, as a solution,
Hey, Dr. Sharjesh,
Yeah.
I think in the x equation, shouldn't the sine term still be negative?
the sign negative. When we integrate, oh, no, when we integrate cosine, we get a sine, right?
Just sine, right? There's no minus sign. If you integrate sine, you get minus cosine.
Oh, yes, I think so. Okay, let me think again. Okay, so this was this, x minus x naught, and this is v naught t, and cosine integrated out, that's sine, so that's a minus sign. You're right. Yeah, correct. Correct. And this one, is it correct now? So, okay. So, so sine integrated gives you minus, right? Okay, so it seems okay. So let's stick to that. We'll see if there's any mistake. Okay, so my solutions are x as a function of time is equal to v naught some velocity, which is decided by electric ratio of electric and magnetic field, minus this is some radius r times sine omega t. Okay. Why is it minus? Is it minus?
I would assume it's just because of the way that you chose the direction of your electric and magnetic field. If you had chosen it in the negative y direction, it probably would have gone to the right, maybe.
It should go to the right, right? Okay, we'll see. I thought it should be, okay, we'll see. Okay, I'm a little worried, keep track of it, okay. Dy is nothing but r, y naught is r, right? So that's r. Minus r cosine omega t. Okay. So at time t equal to 0, y naught is equal to 0. That's correct. And at x equal to 0, that's also correct. But now, of the moment I start moving, there is a small time here. But then the point is which one is larger, right? Yeah, actually this is correct, minus, yeah. Because the first order actually cancels out this one, and then the second order that makes it go. So I think it still goes to the right, we'll see. Okay, okay. So that's your solution, but how do we interpret this, right? This, yesterday, last class, this was proposed that this is actually a cycloid. These are equations of a cycloid, so how do we see this, right? So let me go up, keep the solutions in mind, and let's see how things look like. So let's think of this is a ground, and that is a circle. So that's the elongated circle, but yeah, bear with me. And this is rolling without slipping. So rolling means at every point, the amount of distance it will go horizontally is exactly equal to the circumference of the circle. So after a while, when it reaches here, this is 2 pi times radius r, right? By the time it has traveled this distance, that's 0, it would have gone exactly one revolution, right? So that's the idea. So it's just rotating. If that is the case, then its linear motion is equal to the rotational motion, and it's related by omega c r. So this is v naught. So it's moving horizontally with linear velocity v naught that we said is e over v, and it's equal to angular frequency times radius r. Okay, so that's the center of the circle. After a while, this will get switched. Circle, and this point here would be somewhere here, right? So by the time, so this is your new center, and let's think of how much it has rotated, right? So that's your angle theta. How much it rotates, so that's your theta is equal to omega c times t. Okay. This is radius r, that's also radius r. And let's see how, so this is your point xy. So this is the point we are interested in, that's x comma y. That's x comma y. This point here. That's x comma y. What's the distance it would have gone? So x is equal to, so if I want to calculate x, I need to know how far it has gone here, and then subtract out the x component of this, right? So how far has it gone? It depends on your drift velocity, so it's v naught times t. That's this point, right? That's how far the center has gone. But then I have to subtract out this distance here, which is r sine theta. So that's minus r sine theta. But theta is omega ct, which is exactly what we got. So we did get our sign correct, right? Christian, you were worried, so it should be minus. It seems like, oh, at time t equal to slightly positive, it is going backward. It is not, because the leading order cancels out. The sign has an expansion, so the leading order cancels out, and the next one is positive. So that's okay. So that's your x, and y is simply how far it goes up. So the total distance is r. So the radius of the circle minus the r component. So it is minus r cosine of that. So that's omega c. So that's your equation of a cycle. So how does this look like? So you go like this. So this point is started from here. It went all the way up. So this will go somewhere here to reach the top, and then reach down here. And by the time you reach here, so that's your one full circle. So this was not 2 pi r. So this is 2 pi r. Okay. These are slightly harder than your circle equation. If you know the parametric equation for a circle, you can actually solve for angle theta, correct? So, for example, a circle is x equal to r sine theta, and y is equal to r cosine theta. You can solve for angle theta, you can solve for the radius r. If you square this and add, theta is eliminated. If you take a ratio, r is eliminated. So circle equation of a circle is nice because it can be inverted. Unlike that, cycloid is harder because you cannot solve for angle theta in terms of x and y alone. Right? It's harder to solve. Those equations are not easy to, like, they are not algebraic simple equations. Same thing with radius. It's not a clean solution, but still you can actually calculate. So, for example, you can ask, what is this? What is the circumference or the perimeter of this curve? Right? That's a question one can ask. It turns out to be exactly 8 times this radius r. And those are things that you can think about. But how does our charge move? So let's let me show that. So again, remember your magnetic field is coming out, electric field is going up, right? So electric field is going up, and magnetic field is coming out of the load. So the charge will actually go like this. That's your motion of the charge. and this distance is 2 pi r. Is that visible? Okay. Okay, what else can I say on this? That's all, I guess. Did I give a quiz? Yes, I did. Any comments or suggestion or a change I can finish 5 minutes before? There was a small tiny discussion that came up after last class. I think Christian brought it up, saying about the oscillation of the charges, how it will be, and that is, and I think you guys had a exercise on finding out what a fault track is, right? I haven't looked into your submissions, but Christian forwarded a nice video on that. So, Christian, if you want, you can share it with everyone. Like,
Yeah.
So I'm sure you guys probably looked up also, and you might have come across similar videos. So, is any one of you working in a lab? Gordon and anyone else working in a lab? Matt, Jeremy, Christian, you work in mechanical engineering. So do you happen to work with a Gordon? Not Gordon, fault track? Or you're working in the tangents?
Yeah.
In Dr. Sivakumar's lab, you have a fault track, and do you guys know Chris Mandra? He's a grad student who has a long, nice beard. And he built, like, it was done from the scratch in our department. So he built a fault track in Dr. Sivakumar's lab. So if you contact him, you can see it. So it's basically 4 rods, and in between, so all the 4 pieces have electric field on it for the alternate in electric field, and then you put a magnetic field in it. So I saw it when about 1 year back when he was building the basic pieces on it. But by now, I hear that it is already assembled and it's inside. But most probably it should be possible to take it out or something. I don't know how much Dr. Sivakumar might be interested about. But if you guys are interested, contact me or contact Dr. Sivakumar directly. So it's kind of a cool thing. Okay. That's all. Jeremy, are you planning to do any research, or you're just going to be taking courses?
I'm sorry, what?
Jeremy, I was asking, are you planning to do any research, or it will be just courses that you're planning to finish?
This semester I was going to keep it as simple as possible and see how it goes, because I'm a manager at McDonald's, so I don't really have a whole lot of time. But if I can squeeze stuff into it like next semester, that would be kind of cool.
So you're a manager at where? What did you say?
I do management at McDonald's because I just kind of ended up there, but.
Okay. So that means that's a lot of load you're taking, right?
It's not too bad.
Okay. Once you become a manager, you learn to deal with it. And Matt, do you do work in the university, right? Last time you said you were working.
I work at the I guess I worked at the rec center. I haven't worked there since March, but I've talked to some people about maybe working in a lab or something, but I've never really gone through with it. But it's something I'd be interested in.
Okay, so I'll find out if Gordon, you should also ask if we have some
Open space.
for
Yeah, I'll see. There's me and 2 other people.
that means that's already full, right?
Probably.
I'll check with Sivakumar. I think he usually
I think he does.
because
That'd be cool.
okay, good. Enjoy, guys. Yeah. Thank you.
Dr. Sharjesh, on that video you sent me, did you understand what I was saying about like the single metal loop?
Yeah, it's not very obvious to me as to where the magnetic field is coming in from, or where the electric field is coming from. But my guess is that that is the electric field. It has to be. Magnetic field won't be so powerful, and probably I don't even know. Can oscillating magnetic field do the same thing like if you were to oscillate the magnetic field instead of the electric field? Probably yes, but I'm not sure. Like usually for graph you work with oscillating electric field. It's much easier to put it like that.
Yeah, that makes sense. I was just wondering if maybe, because I couldn't understand how there wouldn't be, like, if they're running electricity through the single metal coil, if it was AC, then you have to have an oscillating magnetic field. So I thought maybe they were just using magnetic particles to show the effect, and it was not like in, you know, exactly a Paul trap, but just kind of similar. But yeah, I don't know. I can look more into it. I just couldn't really find anything like, I was trying to look it up. I couldn't really find anything on Paul Trap that was like that. But I mean, I understand the concept, but it was just the video itself was kind of, I wanted that specific example, I guess.
It can also be that this loop itself is like an antenna. Like it's just voltage is changing, and the magnetic field could be the magnetic field of the Earth. Probably. Right? I don't know how strong that is. Is that sufficient? Is that okay? Let's see. If we want to track it, isn't there a condition here? We would like the oscillations to be oscillations times the radius. The radius in those pictures, that video is about 1 centimeter, right? Probably. So that's 1 centimeter. And what's the E over V you need, right? So this is, can you see what I'm writing? Yeah. So this is E, so this equation, E over V has to be equal to omega C and R. So the magnetic field has to be equal to E over omega C R. So if I want to use the Earth's magnetic field, that's 10 raised to minus 4 Tesla, right? So how much should I need this? Typically, omega C is about 100 or 1,000, right? And this is more massive, so probably even smaller. So if I have the appropriate electric field, I should be able to balance it. So we might be able to use the magnetic field of the Earth itself by field.
But then you would have to know the direction of the magnetic field, right where you're at, right?
So my guess is that just because it's so small, there is a magnetic field for somewhere close by like that. And the electric field is, this is just a positive one plate. So this is like grounded. This is just grounded. And put some voltage. It won't be a constant electric field. It will be weird, but then it has what it also.
Okay.
As an experiment, okay, but for a precision experiment, probably you want it flat and those kind of stuff. Maybe that's my, I'm equally, I haven't read about that particular experiment so much, so I don't know. But yeah, but I've seen the video that you sent me. That's a newer one, but that mechanical one, I was aware of that. That was that's the first time when you that example really explains it very well. Right? You move a parabola or a saddle when you rotate it, it does the job. And this is exactly how an inverted pendulum works. Are you aware of an inverted pendulum?
I don't think so. What is it called?
An inverted pendulum.
Oh, inverted pendulum.
Inverted pendulum. So its idea is very neat. If you have a simple pendulum, it oscillates and there is a stable point, it's at the bottom, right? So you move it and it comes back then, right? Now the idea is that on the hinge, right? If you have a hinge, now you oscillate the hinge. Okay? Not horizontally, vertically. You can try this with a if you have a rod, sometimes you balance a rod on your hand. So you can see that if you put a rod on your finger and try to balance it, if you're looking at it, you can actually balance it. Like you try to see where it is falling and you give a feedback to it. But that's feedback. Here I'm not talking about feedback. So now have the same pendulum, it's rigid in the sense it can go all the way up. And now if you drop it, it will fall back. We all know it. You cannot balance. But here is a cool thing. At the bottom, you start oscillating this bottom hinge of the pendulum. Okay, and in the beginning, for small oscillation, nothing happens, it will again fall. But if this frequency increases, there is a critical frequency, typically for about 1 meter long rod, it's about 22 hertz. Right? If it crosses that 22 hertz, it will actually balance it, it will be stable there. Even if you push it, it will come back. Very cool. So that's an inverted pendulum. Do you know Dustin in our department?
Dustin, he goes to the seminar sometimes.
That's correct. That's exactly right. So he's a grad student, and I am always interested in this. So I had these small tools that I used to play around with it for the inverted pendulum. So I gave it to him, and then he kind of developed it in his own way, and he made a nice, simple inverted pendulum. So maybe I should ask him to present it. Maybe I should ask him to give a talk on in the spot query seminar.
Yeah, that'd be awesome. Yeah.
Presented, or it's not presented. We actually sometimes there are these students from high school show for visiting our department. So he made a nice simple setup and explained to the students. So I kind of like that because I'm interested in the neutral craft, right? Which is harder to do. So the charged particles in the craft, the neutral crafts are not very common. Like there are very less techniques to do that. So as I mentioned in the email, so the idea is that since I think 2010, I have this idea that you can trap it in passing. But I never got too far. 2013 and 14, I worked a lot with John, but then shut at this point. But it's good, cool things that work, yeah. So
I actually, yeah, I found a couple links on kind of like how to build particle traps at home, basically, or just like, cheap, whatever. So I kind of want to put like a material list together. I think that would be kind of cool just to put together. Maybe I'll talk to Chris and see or see if I can come see his if it's still around. I think, yeah, it's interesting. I like how that works.
I haven't seen him this semester. He might have left. He was supposed to leave in summer itself, but then he stayed for one more semester. But we should be able to discuss this with Siva. Just yeah, whenever you're free. You seem to be having too many things in your hands. Like you're the manager of else, that itself is taking a lot of time. It's right.
Yeah, it's been.
I'm sure all this experience is contributing.
It hasn't been, yeah, it's been a little time consuming lately, especially with all the COVID regulations. Now that they're lifting again, now we have to go back into a little bit more business. So it's taking a little bit more time. But once I think it gets going, it'll kind of take care of itself a little bit more. It's just been a little bit, yeah, a little bit more hands-on lately. Just trying to get everything.
But it's good that you're doing it. I appreciate it. Do you get paid at all? Probably not, right? And this is just you're the president of the what do you call it, chapter.
Yeah.
But it's an experience. I'm sure all this contributes. I believe in the fact that all these converge at some point, and all this are useful. It's a part of education.
Yeah.
But it's a lot of work.
Okay. And yeah, so Friday will work for you. Is that to meet about the code?
Yeah, that's it. Okay. There is no department talk on Friday, to my knowledge, so that's okay. But I know that April wanted to talk something about general stuff on Optimum. So let's say Is it possible that we meet after class on Friday? But with a small flexibility that if needed, I will work with April and then get back to you. Is that okay?
Yeah, that's fine.
Or I'll try to reply to your email after talking to you. Then,
Sounds good.
so yes, I am free, but I'm not very sure if I'm already committed. That's fine.
Yeah, no worries.
Okay, good.
Okay, I'll see you Friday then.
Okay, good. Yeah, good.
Okay, thanks. Bye.